Now we talk about a radian. We have a circle, and a radian is an angle such that the arc distance is equal to the radius. Excuse me. So let's take this angle right here. Okay, this angle in here between these two segments. Now, what's the arc distance? The arc distance is out here. It's about this far, isn't it? And the radius is about this. Now, which is bigger, the radius or the arc distance? Very clearly, the radius is bigger than the arc distance. Now, let's take this bigger angle here. Okay, we got the same radius, but we got an arc distance that goes all the way from here to here. Now, what's bigger, the radius or the arc distance? Well, the arc distance is clearly bigger. Just from here to here on a straight line is greater than the distance. The length of a straight line segment from here to here is greater than the radius. So the arc is clearly then bigger than the length of the straight line, because the shortest distance between 2 points is a straight line. And it's just obvious from looking at it, the arc is a lot longer than this line, which is a lot bigger than r. So we have an angle here, small angle, where the arc is less than the radius. We have an angle here where the arc is bigger than the radius. Now in red, we've got an angle, and we got the arc, and the arc is pretty close to being equal to the radius. Okay, the distance along this arc is equal to the radius, or supposed to be. Now you could draw it a little better than I have, but it's plausible that the arc and the radius are about the same length. And if they are the same length, then we say that this angle is 1 radian. Okay, 1 radian is the angle where the arc is as long as the radius. So the characterization of a radian is the arc distance is equal to the radius. The arc distance for this smaller angle is less than the radius, so that's less than 1 radian. And you could estimate what fraction of a radian that is. It looks like it's less than half a radian. This distance is probably less than half the radius, maybe 0.4 times the radius. That would make this angle about 0.4 radians. Now this angle out here looks like it's best part of, you got the radius here. If you did another radius here, it looks like this is pretty close to 2 times the radius. This arc is about twice as long as the radius, which would make this an angle of about 2 radians. But in any case, the arc is bigger, is longer than the radius, so the angle is greater than a radian. Okay, the happy medium, the 1 radian angle is the one where the arc is equal to the radius. Okay, and then I say a couple other things. 1 radian is less than 60 degrees, but not much less. Now, how do I know that? Well, if I wanted to make this into an equilateral triangle with these 2 red sides, if I straightened this one out, that would push this one back a little bit, and I'd have 3 60-degree angles here. So this would be 60 degrees. But in straightening this out, I would push this one back, and the angle would get a little bigger. So the angle would have to grow a little bit to be a radian, to be 60 degrees. So a radian is a little less than 60 degrees, but not a whole lot less. You don't get a whole lot of extra distance by straightening this arc out. You do get extra distance, though. Also then, how many radians is it around the circle? Well, a radian's a little less than 60 degrees. How many times do 60 degrees go in to the circle, the 360 degrees of the circle? It would be 6 times, right? Now, a radian is a little smaller than 60 degrees, so it would go into the 360 degrees a little more than 6 times. 60 degrees goes into 360 degrees 6 times, so you would have a bit over 6 radians to go all the way around the circle. Now, 6 radians is a pretty good approximation, but if you're doing a bunch of revolutions, it's not going to be a good enough approximation. So we want to get the exact approximation. So it's something over 6 radians around the circle. Now, how many radians is it around the circle? Okay, well, you've got an arc that's equal to the radius. Now, in order to get all the way around the circle, you're going to have to put arcs together to go all the way around. How far do they have to go? Well, all the way around the circle is 2 pi times the radius. So How many arcs of length r does it take to go all the way around? An arc of the complete circle has length 2 pi r. That means it takes 2 pi arcs of length r to cover the circumference 2 pi r. That should be very obvious. And 2 pi is what? Pi is 3.14, 2 pi is 6.28, to 3 significant figures. So 6.28 is a little more than the 6. We said it's a bit over 6 radians around the circle. Now it's approximately 6.28 radians, and that's a bit more than 6. So that's consistent with what we've seen and what we should understand about a radian. And you should be able to explain this anytime, any place. Wake you up in the middle of the night. I'm not going to do that. But somebody wakes up in the middle of the night, asks you, can you explain a radian? Boom, you can give them the explanation, get back to sleep before you know you've explained it. Okay, that'd be ideal. Okay, well, this means then that the central angle for a circle is 2 pi radians. Okay, in other words, central angle from here all the way around has to be 2 pi radians because it's 2 pi radii around the arc of the circle. Now there's more. 2 pi radians is 360 degrees then, okay? Because the central angle is also 360 degrees. And that's going to be very convenient. So, let's go to another question. This omega naught, that's 5 revolutions per second, what is that in radians per second? Well, think about it now. Central angle for a complete circle is 2 pi radians. That means if you go through 1 complete revolution, you've gone through 2 pi radians of angle. So a revolution is the same as 2 pi radians. Well, then 5 revolutions per second, we replace revolution by 2 pi radians, you have 5 times 2 pi radians per second. And you multiply that out, it's 10 pi radians per second. Similarly, 2 revolutions per second is 2 multiplied by 2 pi radians per second, which is 4 pi radians per second. So we have the same angular velocities we had in the first problem, the 5 revolution per second and 2 revolution per second angular velocities, now expressed as 10 pi radians per second or 4 pi radians per second. And of course, now a revolution is also 360 degrees, right? So 360 degrees instead of 5 revolutions per second is 5 times 360 degrees per second. That's 1800 degrees per second. I mentioned that earlier. And 2 revolutions per second would be 2 times 360 degrees per second, which is 720 degrees per second. Okay, you can ignore this polynomial. I wrote that down for another class. Your assignment is going to, well, it's already up. It includes some work with radians and so forth, and also some work with reasoning out angular quantities.